Section 4.2 is the mean value theorem. So this is a fairly interesting theorem on its own, but it turns out to be a pretty key part of the fundamental theorem of calculus, which, as it sounds, is a pretty fundamental part of calculus. We'll see that later on in chapter 5. Now, the mean theorem, we worked to it through a theorem called Rolle's theorem. So a lot of this stuff really, it won't feel like, just rote mechanical, working through solutions to problems like a lot of other calculus sections have felt in the course so far. But it'll be a little bit more conceptual, a little bit more theoretical. It's important that we understand at least some of the basics of these theorems, because these are the blocks that build up all the apparatus that we use in calculus for all the calculation and computational type problems that we do. So it's really sort of key to understanding the theory of calculus to understand a section like the mean value theorem here. So to start with the mean value theorem, we have a special case of it called Rolle's theorem. So if f is a function that satisfies the following three conditions: one, f is continuous on the interval a to b, the closed interval a to b. It's differentiable on the open interval a to b. F of a is equal to f of b. Then we can conclude that there's a number c in the interval a to b such that f prime of c is equal to 0. Oh, that's interesting. We can conclude that f has a critical number in the interval a to b. That's another way to put that. So what were the two conditions? Let's look here. We're talking about an interval a to b and some function y equals f of x. So I've got a blue function here, f of x. I've got a red function, g of x, two different functions. The first condition is that they're continuous. Either one of these is continuous. Well, g is continuous on the interval. F is continuous on this interval. So that looks good. That condition's met. F is different. The function is differentiable on the open interval. Well, both of these functions are smooth. There's no kinks or corners, breaks or discontinuities, right? So they're both differentiable on this interval as well. The third condition is that f of a is equal to f of b. Now, this isn't drawn very well, but this is supposed to be at the same height, this intersection point, as the one on the left. So this and this are at the same height. So it should be the case. In other words, f of a is equal to f of b then. Same thing for g. G of a is equal to g of b. So in other words, we start and finish at the same y value at the ends of this interval. Okay, and look at either of these cases. It looks like the function y equals f of x has multiple places where its derivative is 0. Remember, the derivative is 0 anywhere it has a horizontal tangent line. All these local minimums and maximums, minima and maxima, are places where we have f prime of c is equal to 0. On the other hand, g of x, it has only 1, but it has at least 1, right? All the theorem tells us is that there is at least one number c, right? Or there is a number c in a to b such that f prime of c is equal to 0, such that c is a critical number. So this one looks like it only has one such c, but both do. And it wouldn't matter how we drew this. If we had another case like this, we'd see there's one here, right? So Rolle's theorem is a pretty intuitive thing. If we draw these, if we do a sketch, try to make counterexamples to defeat the theorem, you'll realize that it's impossible to do because, well, the theorem is true. It is a theorem. All right, so let's see what we can do with this. All right. So the first example we apply it to regards a position function, s of t, right? A position s, distance away from some origin at a time t. It's the position function of an object. Okay, yeah. We'll assume that s of t is differentiable on a to b and continuous on a to b. Those are the first two, the closed interval a to b. Those are the first two conditions of Rolle's theorem. And next they ask us to show that if the object is in the same position at times t equals a and t equals b, so s of a is equal to s of b then, so they're telling us here that's in the same position, then it must have stopped moving for at least one instant between the times a and b. So that's an interesting thing to be able to show about a physical scenario. Whatever this object is, it has position function s of t. It's differentiable and continuous, which many descriptions of or mathematical models of something moving has a differentiable or have differentiable and continuous functions modeling them. And at t equals a and t equals b, it's in the same position. These are all the conditions of Rolle's theorem. So let's see how we go about doing this. Right? All three conditions are met. Rolle's theorem tells us that there exists a t value that's equal to c, or sometimes c, in the interval a to b, such that s prime of c is equal to 0. Okay? Well, that means that the derivative of s is equal to 0 at this point. Well, s is a position function. The derivative with respect to t, or time, of a position function is a velocity function. So at some point, this velocity function, s prime, is equal to 0. Well, if something's derivative is equal to 0, or if something's velocity function is equal to 0, then its motion is, well, it's not moving at that point. If it has 0 velocity, it's not moving at that instant. Therefore, the object stopped moving for one instant in this interval. And that was at the instant t equals c. All right, and this is c is just, we don't know what value that c is. It's just, we know that it exists by Rolle's theorem. There is such a c, and Rolle's theorem guarantees it based on those conditions. Okay, another use of this is more mathematical and less of a modeling situation. Show that the equation x cubed plus x minus 2 equals 0 has exactly one real root. The hint here is you'll need to use the intermediate value theorem as well as Rolle's theorem. Okay, one real root. Well, we remember this about cubic polynomials, right? If I just look at this side, I know this function is going to be equal to 0 somewhere because its in behavior for a cubic is right and up and left and down. So it's got to pass through the line y equals 0, or the x-axis somewhere. In order to guarantee it mathematically or in another way, we can use the steps that follow below. So it's continuous over all real numbers. First things first, this function is. So we consider, for the sake of the intermediate value theorem, I plug in -1, f of -1, and I get -4. That's a number less than 0, right? Now I have f of 2. Right? When I plug that 2 in, I get a +8, which is greater than 0. So I have two numbers I can plug in, -1 and 2, into my function to get a negative value and a positive value. This function's continuous. It's a polynomial. So I know that it attains every value between -4 and 8. So between -4 and 8, it attains every value between those because the function is continuous. So I know it passes through 0. So I know that my root is between -1 and 2. Somewhere between these two x values is a number that when I plug it into f gives me 0. That's old news, right? That's chapter 2, I believe, with the intermediate value theorem. Okay, and that's what we're summarizing right here. There exists a c in -1, 2, such that f of c is equal to 0. In other words, there's a root. So it has at least one root. Okay, so we know that we've proved that part of the problem. They asked us to show that it has exactly one real root, though. All we've shown so far is that it has at least one real root. We don't know if it crosses multiple times, something like this, at the x-axis, or if it just crosses once. Well, it must cross once because they're telling us to prove that it has just one real root. So in order to do that, what we can do is this. We could say that, suppose, this is where Rolle's theorem comes in. Suppose f has two roots, c1 and c2, we'll call them. And note that as roots, f of c1 is 0, f of c2 is also 0. They're both roots. They both make this function equal to 0 when we plug them in. So now we have two endpoints that match, right? This is an a and a b, essentially. c1 and c2 here is our interval that we're interested in, okay? F is differentiable, which means it's also continuous. Again, it's differentiable and continuous because it's a polynomial. So this condition here, as well as the fact that f is differentiable and thereby continuous on the interval c1 to c2, means that Rolle's theorem is applicable. So if that's the case, we know that there exists a d this is by Rolle's theorem, such that f prime of d is equal to 0. So the derivative of the function f is equal to 0 at this value d. So Rolle's theorem tells us if this is the case, if the function has two roots or more than one root, and this would be two of them, right, then f prime of d is equal to 0 thanks to Rolle's theorem. Well, what's f prime of x? We take this derivative real quick. We get 3x squared plus 1 from f. This is our 3x squared plus 1. If I set this equal to 0 and try to solve for it, well, look what happens when I solve for x squared. I get x squared is equal to negative 1/3. Well, the solution to that is 1 over root 3i. That's an imaginary number. That is not a real number. There is no real number, right? Such that, that's a root of this equation right here. So there is no d. This contradicts, or this gives us a contradiction with Rolle's theorem, right? This is not a real number. We don't have such a number. So this assumption that there was a C1 and a C2, two roots of this function, or more than one root, and these are two of them, this assumption forces something like this every time, contradiction with Rolle's theorem, and contradiction can't stand, so there cannot be more than one root. So we know that f has exactly one real root in this case. That is a fairly sophisticated argument, especially for a Calculus 1 course. If you can follow the logic of it, that's fantastic. This is a good thing to see. Try to understand it is what I would suggest. I don't think that there will be many occasions where you'll have to reproduce such an argument. This is getting into a 200 level mathematics type of material. Let's go see some more direct examples and meet the mean value theorem, which is still relatively easy to understand. So let f be a function that satisfies the following. It's continuous on the closed interval a to b, just like Rolle's theorem. Differentiable on the open interval a to b, just like Rolle's theorem. I mean, those are only two assumptions, so that's interesting. We don't have to match at the endpoints anymore. The mean value theorem guarantees that there's a number c in this interval such that f prime of c is equal to f of b minus f of a over b minus a. Okay, that's pretty much a mouthful here. Another way of writing this is saying that f of b minus f of a is equal to f prime of c times b minus a. Now, this is still, again, kind of a complicated looking scenario, but let's consider this. Let this be the function y equals f of x, this blue curve that I've sketched right here, right? So the mean value, and here's a and b, our interval. This function is smooth, right? So it's differentiable and therefore continuous along the interval a to b, closed and open, respectively. So if I consider f of b, a and b, right, our endpoints, a f of a here, b f of b on the right, these are these 2 points. If I talk about f of b minus f of a over b minus a, what am I actually calculating? That's the slope. It's the change in the y values of these points minus the change in the x values. It's the slope of this line that connects those 2 points. So that's very interesting. Now, what does the mean value theorem tell us? It guarantees that there's a number c somewhere in this interval between a and b such that f prime of c is equal to the slope of this secant line. So in other words, it guarantees that there's a tangent line somewhere on this curve that's parallel to the secant line. In this case, I drew it so that there are 2 of them, but there's not necessarily always 2, but there's at least 1. And this is our case. So that's a really nice fact to have. And it's a key part of the link between integral and differential calculus that we'll see later in chapter 5. So now here are some problems and some things that we can do with it in order to get familiar with it and to understand it through some exercises. So verify that the given function satisfies the conditions of the mean value theorem on the given interval, then find all numbers c which satisfy the conclusion of the mean value theorem. Okay, now this is sort of a rote, get after it and solve it type problem, okay? So I look at this function, and we're talking about f of x as the rational function x over x plus 2 on the interval 1 to 4, closed interval 1 to 4. Now, I look at that and realize this thing only has a domain problem that x equals -2. So -2 is not in this interval, so I don't have a domain problem anywhere. This thing is differentiable and continuous on this interval, no problem whatsoever, not even a hole in its domain. So we're all set to apply the mean value theorem to it. Quickly, I'll just say off to the side, let me rewrite this as a product, x times x plus 2 inverse instead of dividing by it. That way I don't have to use the quotient rule if I don't want to. Yeah. So we pointed out the domain of f is this, since we're talking about 1, 4, and the function is continuous and differentiable there, then yes, as a rational function, that's the case. All the conditions of the mean value theorem, or both the conditions, are met. It's continuous and differentiable on this interval, we've stated. Now, what's the slope of the secant line? So we calculate that first. We're trying to find all the values c within 1 and 4 that satisfy f prime of c is equal to this number. So we just need to plug it in. Well, b is 4 and a is 1. So f of 4 minus f of 1 over 4 minus 1. Well, f is x over x plus 2. So I've got 4 over 4 plus 2 minus 1 over 1 plus 2 for these two values. And when we simplify all that arithmetic, we end up with 1/9. So moving on, what we want to find now, what the problem's asking us to do, is find all the x values for which f prime of x is equal to 1/9. What I need to do is find the derivative of my function f. In either case, if you like the quotient rule, you could do that. I've written it like this, so I could use the product rule with a chain rule. F prime of x is this expression, right? You can work out the details of that. And I'm solving for 1/9 being equal to this derivative. Now let's see. It looks like in order to get a little ways along this, I've multiplied both sides of the equation by x plus 2 squared, right? That's to cancel with this term and this one. And what I see I have left is x plus 2 squared times 1/9 on the left-hand side here. And that's equal to x plus 2, because x plus 2 squared times this leaves us with an x plus 2 to the first, what we had below. And then I have minus x, right? And that was just because this canceled with that. Now, I think I just have an artifact in here because this is not equal to 2. There's no reason to have equals 2 here. So let me just go ahead and strike this out. I'm not sure if that was a copy paste or erasing error, but that should look just like this. We should be fine. What we need to do is expand the left-hand side, this squared term right here, and then combine all like terms. Oh, sorry, I see what I did. Let me come back to that. X plus 2 minus x is 2. Okay, so the right-hand side simplified. We'll multiply both sides by 9 and get x plus 2 squared equals 18. Then we'll expand. So let's see that on the next page. Yeah, x plus 2 squared is 18. Multiply both sides by 9 to get rid of the 1/9. Now, square root of both sides is plus or minus root 18. X plus 2 equals that. X is -2 plus or minus the root 18. Square root of 18 has, well, 18 has a perfect square 9 as a multiple. That comes out as a 3 from the radical. So it's plus or minus 3 root 2 minus 2. These are our two numbers that will satisfy f prime of either of these numbers is equal to, what was that, 1/9, I believe? Is equal to, yes, 1/9 right here. These are the two numbers that satisfy it. What we have to do is make sure that they're both in this interval. But they have to be between 1 and 4. So we know right away that -3 root 2 minus 2 is negative, and it's not in the interval 1 to 4. So we throw that one away. So now I'll claim, as my answer, I'll claim that 3 root 2 minus 2 is in 1, 4. And we've already shown or seen that f prime of that number is equal to 1/9, which is equal to this side. So this is our link. F prime of a number equals the secant line slope. our tangent line slope is equal to our secant line slope through this one night. So we found the value that does that. I've claimed that this number here is in this interval. Now, if I have a calculator, I can show that pretty easily. If I don't have a calculator, I can still do it, right? Here's a nice way to see that in case you don't have a calculator handy. So I'm going to check my claim by just placing this in this inequality and say, well, I'm telling the reader that this is in the interval 1 to 4. So if this number is between 1 and 4, then it satisfies this inequality, of course. Now I'll start to sort of solve this for root 2 to make sure that what I get as an equivalence after line by line, an equivalence that, something that makes sense to me, right? Something that works out in a way that we can clearly see. Add 2 to all sides, and we're left with this in the middle. 2 plus 1 is 3, 2 plus 4 is 6. So we have these new left and right boundaries. Divide by 3 on all sides. So we're left with root 2 in the middle, 1 and 2 on the right. And at this point, we probably remember that root 2 is between 1 and 2. If we're still not sure, we can square all sides. We have 1 squared is 1, root 2 squared is 2, and 2 squared is 4. When I look at this, I see an inequality I fully can confirm. 1 is less than or equal to 2 is less than or equal to 4. That checks, right? That's consistent with true mathematical statements. So this claim is in fact correct. So anyway, a calculator could do that just fine for you. But it is nice to know how to do that in case you don't have a calculator handy. That's one nice way to go about it. So moving on, we suppose that a falling object has position function s of t equals 4.9 t squared, where s is measured in meters and t is time in seconds. First question asks us to find the average velocity of this object between times t equals 0 and t equals 2. So the average velocity, that's really easy to do, right? We just do s of 2 minus s of 0 over 2 minus 0, our 2 times of interest for our average along that time in terms of velocity, distance over time, change in distance over change in time. And we have, well, this works out to 9.8 when we're done canceling everything, and that's meters per second. So there's our average velocity. Now, the next part of the question asks us to show that there exists a time in 0 to, the interval 0 to 2, at which the particle has exact velocity equal to this average velocity. So if we think about this, think about traveling, right? If you travel an average velocity from destination A to destination B, maybe you're driving a car, and you average 60 miles per hour on your drive between here and maybe a neighboring city, right? Well, at some point during your drive, you went exactly 60 miles per hour, guaranteed, right? That's all we're really showing here in question 2. So that's an interesting thing to keep in mind, a nice connection point. So we have to note some things. 4.9 t squared is a continuous function on the closed interval 0, 2. It's polynomial, so it's continuous. Also, it's differentiable on the open interval 0 to 2 because it's a polynomial. It's differentiable everywhere. The mean value theorem then implies that there exists a c, some number, in 0 to 2 such that s prime of c is equal to 9.8. So we know without ever even looking for it that at some point, if this thing travels at an average speed of 9.8 meters per second from time 0 to time 2, well, then we know at some point it went exactly 9.8 meters per second. That's what this line down here is telling us. Okay, and then the last step, you've probably anticipated it. Find the time t for which the particle's instantaneous velocity, the exact moment, is equal to its average velocity. So when exactly did this thing travel at its average velocity for that instant? Okay, well, v average was 9.8. We're going to find c in 0, 2 such that s prime of c is equal to 9.8. So what we do is we need to take s of t and differentiate it to get s prime of t. We have that here. And now we set s prime of t, this, equal to 9.8. Well, that's 9.8t, or in this case, 9.8c, because we have S prime of C. Just a little change of variable there. It doesn't really matter. It's just a dummy variable. Well, we solve for C, and that's a really easy equation. 9.8 C equals 9.8. Divide both sides by 9.8. We have C is equal to 1. And that's in the interval 0 to 2. Clearly 1 is in the interval 0 to 2. So at the instant time is the second number 1, this object moves at exactly 9.8 meters per second. And that matches its average velocity from time 0 to time 2. Again, you can connect that to a drive from here to maybe Los Angeles, and you average 60 miles per hour. At some point, you're guaranteed to have gone exactly 60 miles per hour. You might not go 60 miles per hour the whole time. You might spend half your time going 65 miles per hour, and the other half of your time exactly going 55 miles per hour. But to get to 65 miles an hour, you crossed 60 miles an hour. To get back to 55 miles an hour, you crossed 60 miles per hour. And there you have it. Okay, so some last little results that are interesting and nice to work with are the following. F prime of x, if f prime of x is 0, for all x in an interval AB, then f is constant on that interval AB. So let's think about that. If the derivative of a function is 0 for all the values in that interval, in a given interval, that means the function has a whole bunch of horizontal tangent lines the whole play everywhere. And if that's the case, well, then of course it's going to be a horizontal. It's going to be constant, or a horizontal line for that section of the x-axis. Right. This is proved with the mean value theorem, with an application of the mean value theorem. We won't really go into the details of that, but the book surely contains it. Corollary to this, if we have two functions whose derivatives are the same, f prime of x is equal to g prime of x for all the values in an interval a to b, then the difference between these two functions, f and g, f minus g, is constant on AB. So in other words, we can write f of x as g of x plus c, where c is some constant. Okay, so what that tells us is that if two functions' derivatives match for all values in a given interval, then they're only different from each other by a constant, because all of their tangent line slopes are the same. They're the same shaped curve. They're just shifted up or down from each other. Okay, so for instance, let's look at this. Let's take f of x equals sine x, g of x equals sine x plus 4. We'll all agree that this function is 4 units below this function. This one's been shifted up by 4 on the vertical axis. Well, the graph of y equals sine of x looks like this, okay? And the graph of g of x, where y equals sine of x plus 4, is up 4 units, it's above it, but everything else is the same. It's been rigidly transformed. It's the same curve as the one below it, it's just a few units above. What's the derivative of each of these functions? F prime of x is cosine x, g prime of x is cosine x. The derivatives match, right? So here we are. We haven't confirmed the theorem. We haven't proved that corollary. We've just validated it for an example, right? So we see that, yes, f prime of x and g prime of x are the same. Well, that means that these two are different by a constant. Okay, we're really starting to toe into the realm of antiderivatives and the fundamental theorem of calculus and integrals. Well, not necessarily fundamental theorem or integrals, but we're getting into antiderivatives to some degree to talk about this. So that's interesting to note. But nonetheless, all we need to think of now is if two functions' derivatives match on an interval, they're the same curve except they've been shifted from each other by some amount. Okay, so the last problem that we'll do here, we have this example at the bottom. They say, let f of x be equal to 2 minus absolute value 2x minus 1. Your guard should be up. Absolute value is now in play, right? Absolute value is not a differentiable function. So we have to keep that in mind. Anyway, show that there is no value of c such that f of 3 minus f of 0 equals f prime of c times 3 minus 0. In other words, show that we cannot find a c value as guaranteed by the mean value theorem. Okay, well, let's get to work on this. What is f of 3 minus f of 0? Well, that's not the first thing I did in the work down here, but we'll go ahead and do that. F of 3 minus f of 0 all the way down here. And we're trying to show whether or not there's a c that satisfies this. Looks like that number, I guess it's irrelevant. We do 2 minus absolute value 2 times 3 minus 1. So 6 minus 1 is 5. So 2 minus 5, we get negative 3, right? And then minus 1. Okay, I didn't do anything with that value right away, is the other part of that. So maybe I got out of turn there for a little bit. Let's go back. We're going to need the derivative of f to begin with. So let's just do that. We're going to have to take this function and figure out whether or not we can differentiate it. We can differentiate it in some places, but it's not differentiable everywhere. Namely, it's not differentiable wherever this function inside the absolute value is 0, right? So, right, we're looking for the derivative of f. Well, let's write f down carefully. This is 2 minus 2x minus 1. We just make this parentheses here and don't change this sign if 2x minus 1 is positive. In other words, greater than or equal to 0. Now, if what's inside here is negative, if 2x minus 1 is negative, then we put a minus sign in front of this, and there's already a minus sign, so minus minus is positive. Okay, now I want to simplify this piecewise function. So I'm going to work downwards to do that. I'm going to simplify my address over here. I'm going to add 1, divide by 2 for the first one, right? To get x greater than or equal to 1/2. I'll add 1, divide by 2 for the second to get x less than 1/2. Now I distribute my minus sign for minus 2x plus 1. And I have plus 2x minus 1 for the second line. And I keep working. And this is negative 2x plus 3. And this one is 2x plus 1. So now I've simplified this quite a bit. That's nice. If I take the derivative of this function, well, I'm going to take it as a piecewise derivative, we'll call it, which has not really been correctly defined. But I could say this. I'd say, all right, f prime of x seems like it's negative 2. I'm going to take the derivative up here. F prime of x when x is less than 1/2 is positive 2 from this line. And the one thing I haven't done a very good job of is right here, maybe in my work or my pseudo work, because this is not really that official, but it's official enough to make the argument. I should just put strictly greater than, because I don't know about f prime of 2, right? What's the derivative as we approach 1/2 from the right? It's negative 2, right? It's positive 2 if we approach 1/2 from the left. Right? If we went into all the details of how we're supposed to actually take a derivative, we'd have a left and right derivative of this function at 1/2, and we'd see that the derivative doesn't exist. So this one does not exist. Okay, so we'd have to be rather careful with that. Okay, now it might not matter, right? So I'm just gonna keep that there. We've already seen problems like that back in chapter 2. It might not matter because what we can do is we're gonna plug in 0 and 3. So it shouldn't matter, right? Or possibly, we're not gonna plug in 0 and 3, but we're going to look for a value that can satisfy what this condition is going to impose on us. Okay, so f of 3 minus f of 0 is the left-hand side. C is yet to be determined. F prime of C is yet to be determined. And we have 3 minus 0 for the B minus A part. All of this, of course, comes from what they're asking us to confirm or disprove here. Okay, so when we simplify all of this, we get down to negative 4/3 equals F prime of C. I'll let the student take their time with that and work out the details down here at the bottom and just confirm that all of this is correct. This is plugging in 3 to F. This is plugging in 0 to F. That absolute value function, or that function involving absolute value. This is just 3 minus 0 for a multiple of 3. But we see that -4/3 is equal to f prime of c, and we're looking for a c in 0 to 3 that does this. Here's the problem. We just calculated f prime of x, right? So we're not really, so for one thing, it can't be this value, can't be c equals 2, because that derivative doesn't even exist. But that's not really the main issue here. The main thing we notice is this. Is there any number for this function, for the derivative of this function, for which the output is not 2 or -2, right? The only derivative this function has is -2 or 2. All of its tangent lines have slope -2 or 2 and nothing else. That's what this tells me right here, right? The work that we did in this place. There's no way for it to ever be equal to -4/3, right? It's not -2x or 2x, right? Something that can cross through that value. It is only ever -2 or +2. Neither of those values is -4/3. So there does not exist a c such that f prime of c is equal to -4/3, right? So in other words, there does not exist a c that satisfies this equation. And the reason for all of this is because, and the reason this doesn't contradict the mean value theorem, right? This is the mean value theorem's conclusion right here. The reason for this all is, as I said at the very beginning, the absolute value is not differentiable on the interval. At least this absolute value function is not differentiable on the interval 0 to 3. Right? So that's just where we're at, right? It's not differentiable on the interval 0 to 3, so there's a known, so the mean value theorem doesn't apply to it. So there's no reason to expect that we can find such a c value. It won't be guaranteed because the conditions of the mean value theorem are not met. So that was ending on a bit of a theoretical one, but nonetheless, work through these arguments, try to understand them as best you can. Something like this is maybe a bit more likely than I think a couple problems ago. I think these were, let's see, these were a bit more theoretical and not likely to be test questions. You should understand them. You'll see them in homework maybe, probably not a test. If I get here, this one, this would be a hard test question, but I think it's a doable scenario, and I think you should see some exercises similar to it in the homework as well. So that's it for the mean value theorem until it comes up again later when we meet the differential calculus, or so the integral calculus.